disclaimer for the viewers.
In the today's session, we are going to discuss methods of preparation of the Niosomes. So let us see the methods of preparation of Niosomes. Niosomes are prepared by using the different methods like Proniosomes Method, Sonication Method, Microfluidization Method, thin film hydration method, reverse phase evaporation, ether injection method, transmembrane pH gradient, then heating method, supercritical carbon dioxide fluid method, and the bubble method. So these are the various methods which are widely used to prepare the Niosomes. We have seen the different methods for the preparation of the liposomes, and the same thing which is we have to supposed to apply here for the preparation of Niosome also. So let us see one by one the details of the each method. Very first method, that is the Proniosomes method. Proniosomes are called as the dry Niosomes. These are the dry vesicles. A dry form of formulations of the non-ionic surfactant vesicles which can be converted into the Niosome after hydration in a short time and are now widely used in the formulation of Niosomes due to their good stability. So in the case of Proniosome method, so Proniosomes are the dry Niosomes, and at the time of delivery we have to suppose to hydrate these Proniosomes. Here in the case of Proniosome, as it is available in the dry form, it improves the stability of the product. So the Proniosome consists of a water soluble carrier coated with the non-ionic surfactant and are easily hydrated into the Niosome before use. So the Proniosome consists of water soluble carrier coated with the non-ionic surfactant and are easily hydrated into the Niosome before use. Look at the figure. So this is the water soluble carrier. So this is the surfactant. It is coated with the carrier. It is coated with the non-ionic surfactant, and we are getting the dry form of the vesicle that is called as the Proniosome. And at the time of the use, we have to suppose to hydrate these Proniosomes. So after rehydration with agitation, we will get the Niosomes, that is the multilamellar vesicles. This method possesses several advantages such as good physical and chemical stability for long-term storage, then convenience for transportation and ease to scale up. So these are the few advantages of the Proniosome method. This technology may offer more options for Niosomes to be further formulated in a different forms such as tablets and gel. As the Proniosome, it is a dry form and it is possible to formulate certain other formulations like tablets as well as the gel formulation. Proniosomes could be used successfully in the application of drug delivery through different routes such as oral, parenteral, dermal, transdermal, and the ocular. So this is the best way to minimize the water content in the Niosome in order to improve their stability and may provide a solution for long-term storage. So in short, the Proniosomes are the dry Niosomes, that is the dry form of the formulations of the non-ionic surfactant vesicles which can be converted into the Niosomes after hydration in a short time. Let us see the sonication method. Already we have discussed enough about the sonication method in the liposomes. So the sonication is a conventional method for preparation of the Niosome. This method is easy to operate. The drug solution that is in the buffer must simply be added to the proper mixture of non-ionic surfactant at optimized ratio and then sonicated at a determined frequency, temperature, and time to obtain the desired Niosome. So simply here, we have to suppose to prepare the drug solution in buffer and add it to proper mixture of a non-ionic surfactant at optimized ratio, and then sonicated at a determined frequency, temperature, and time to obtain the desired neosome. This is also a suitable way to control the particle size of the neosome by changing the frequency, temperature, and the time. Mechanical agitation with sonication improves the encapsulation efficiency. Simultaneously, if we are agitating the solution along with the sonication, it will improve the encapsulation efficiency of the product. Sonication can decrease the diameter of neosomes with a narrow size range. It is also used to reduce the size of the vesicle. Here it is possible to use the bath sonicator or probe sonicator for the preparation of neosome. In the probe sonication, involves the use of high levels of energy and may cause the sudden increase in the temperature and shedding of the titanium into the solution. So this is about the sonication method. It is similar to the method of preparation which we have discussed in the liposomes. Let us move towards the next method, that is known as the microfluidization method. So the microfluidization is a new method for the formulation of the neosome, which is based on jet principle. That is, by mixing two kinds of fluid such as alcohol and water in a microchannel. That's why it is known as the microfluidization technique. So in this technique, the jet principle is used and we are mixing the two kinds of fluid such as alcohol and water in the microchannel. Neosomes can be formulated with the desired particle size and size distribution by optimizing the parameters such as mixing conditions, then the surfactant and the other materials. The size of neosome obtained by the microfluidization method is below 60 nanometer with a relatively narrow distribution and good stability for over 8 weeks at 25 degrees Celsius. It offers certain advantages such as the formation of neosomes with a smaller size, better reproducibility, and ease of formulation. This method is widely used for the industrial development of the neosome. So this is about the microfluidization method. Simply, whatever the solvents are there, which are mixed in the microchannels, isn't it? And here the parameters which are optimized, like mixing conditions, then the surfactants and the other material, and we are getting very narrow size range of the neosomes, and the size, it is just below the 60 nanometer. So this is about the microfluidization method. Let us see the thin film hydration method. It is same like a neosome. Okay, we will discuss the thin film hydration method in brief. So it involves the dissolving the membrane forming material in an organic solvent in a flask. So first step is to prepare the solution of the membrane forming material in the organic solvent. Then evaporate the organic solvent by hand shaking or the rotary evaporation in order to get the film. Then furthermore, we have to suppose to add the aqueous buffer into the thin film along with the drug. Then the hydrate the solution and sonicate it so as to we will get the neosomes. So it involves dissolving the membrane forming material in an organic solvent in a flask. After removing the organic solvent by vacuum evaporation, a layer of dry thin film forms inside the flask. So this is the second step. The drug is dissolved in the aqueous solution such as water, buffer, and then added to hydrate the dry film. The third step. It is incubated about transition temperature of the surfactant in a water bath to form the neosomes, that is the multilamellar vesicles. Sometimes this technique is used together with the sonication to acquire neosomes with a narrow size range. If we require the narrow size range, we have to suppose to use the sonication. It is widely used to formulate the Niosomes loaded with the drugs like insulin, doxorubicin, and certain extracts. So this is about the thin film hydration method. Let us see the reverse phase evaporation method. The reverse phase evaporation method involves dissolving the non-ionic surfactant and other additives in the organic solvent. So very first step is dissolve the surfactants, then the cholesterol, and whatever the things are there in the organic solvent. Okay, so here we will get the organic phase. Then the loaded drug, it is dissolved in an aqueous solution such as water or a phosphate buffer, and then added to the organic phase to form an emulsion under sonication. So first step, to prepare the organic phase with the non-ionic surfactant, then prepare the aqueous phase with the drug, mix these two phases in order to get the emulsion under the sonication. The organic solvent, it is removed by rotary vacuum evaporator at a 40 to 60 degree Celsius to form the large unilamellar vesicle. So once we have mixed these two phases, that is the aqueous phase and the oily phase, initially we have to suppose to shake it vigorously and sonicate it. So here organic phase inside the aqueous phase, that is a O by W type of emulsion we are getting, and furthermore evaporate the organic phase in order to get the Niosomes in the aqueous phase. So compared with the thin film hydration method, the vesicles prepared by the reverse phase evaporation method could yield the nanoparticles with the uniform size and unilamellar or the oligolamellar structure. So whatever the Niosomes we are getting in the case of reverse phase evaporation method, it is of a uniform size and either of a unilamellar or the oligolamellar structure. So in the case of reverse phase evaporation method, we are preparing the two phases. Very first one is organic phase, second one is the aqueous phase. In the organic phase, we have to suppose to dissolve the surfactant and cholesterol. In the aqueous phase, we have to suppose to dissolve the drug. Then mix these two phases in order to get the O by W type of emulsion. Sonicate the mixture, isn't it? And evaporate the organic phase so as to we will get the Niosomes. So this is about the reverse phase evaporation method. Let us see the ether injection method. It is same like we have discussed in the liposome. So in the ether injection method, the surfactants with the additives are dissolved in the diethyl ether, that is organic solvent, and injected slowly through a needle in an aqueous drug solution maintained at a constant temperature which is above boiling point of organic phase. So here this is the aqueous phase which comprises the drug, in the syringe which comprises the surfactant and the cholesterol which is dissolved in the organic phase, and whatever the organic phase is there which is dropped into the aqueous phase at a slow rate. The organic solvent is evaporated using a rotary evaporator, and during the vaporization formation of a single layered vesicle occurs. So this is about the ether injection method. So in the case of ether injection method, we have to suppose to dissolve the surfactant and cholesterol in the organic phase. In the flask, take the water or the buffer and dissolve the drug. Drop the organic phase into the aqueous phase at a slow rate, isn't it? So as to we will get the aqueous plus organic phase. Then with the help of a rotary evaporation, evaporate the organic phase so as to we will get the Niosomes. So this is about the ether injection method. Let us move towards the next method, that is the transmembrane pH gradient. So in this method, the surfactant and cholesterol are dissolved in a chloroform and evaporated to form a thin lipid film on the wall of a round bottom flask. The film is hydrated with a solution of a citric acid, which is having a pH 4 by vortex mixing, and the resulting product is a freeze thawed for the Niosome formation. The aqueous solution of drug, it is added to this neosomal suspension. After that, the phosphate buffer is added to maintain the pH between 7 to 7.2. According to this method, the interior of neosome has it is a more acidic value than the outer medium, as here the film it is hydrated with a solution of citric acid and which is having a pH 4, isn't it? And furthermore, we are getting the neosome. And when we are adding further aqueous solution, which is having a pH 7 to 7.2. So inside core pH, it is 4 and outside pH, it is 7.2. The added unionized drug passes through the neosome membrane and enters into the neosome. The drug ionizes in an acidic medium and cannot escape from the neosomal bilayer. So here it utilizes the pH gradient to load the drug into the neosome. That is a main principle behind the transmembrane pH gradient. Simply, in the transmembrane pH gradient, surfactant and cholesterol are dissolved in the chloroform and evaporated to form a thin film on the walls of the round bottom flask. The film is hydrated with a solution of a citric acid, which is having a pH 4 by vortex mixing, and resultant product is freeze thawed for the neosome formation. So further hydration leads to we will get the neosome. The aqueous solution of drug is added to this neosomal suspension. After that, the phosphate buffer is added to maintain the pH between 7 to 7.2. So the pH outside the neosome, it is near to 7 and core pH, it is a 4. So due to pH gradient, whatever the drug is there, unionized drug is there, it enters into the neosomal core and it gets ionized. So according to this method, the interior of neosome has a more acidic pH value than the outer medium. The added unionized drug passes through the neosome membrane and enters into the neosome. The drug ionizes in acidic medium, that is the internal core, and cannot escape from the neosomal bilayer. So this is about the transmembrane pH gradient. Let us see the heating method. So in the case of heating method, we have to suppose to prepare the surfactant and cholesterol are separately hydrated in a buffer. So here this is the surfactant, this is the cholesterol. So we have to suppose to hydrate the surfactant separately and the cholesterol separately. Then mix these two phases, that is a surfactant solution and the cholesterol solution, by heating and stirring at 120 degrees Celsius for 15 minutes. Okay, so as to dissolve the cholesterol. Then furthermore, the temperature is reduced and the surfactant and other additives are then added to buffer in which the cholesterol is dissolved while stirring continues. So here furthermore, we are reducing the temperature to 60 degrees Celsius for 15 minutes, and furthermore we have to suppose to add the drug and other additives into it. The neosome forms at this stage are left at a room temperature and then are kept at 4 to 5 degrees Celsius under nitrogen atmosphere until use. This is about the heating method. So here we are using the heating to prepare the neosomes. Let us see the supercritical carbon dioxide fluid method. So in the case of supercritical carbon dioxide, here we are utilizing the supercritical carbon dioxide to prepare the neosome. So in this method, the twin 61 cholesterol, glucose, phosphate buffer, ethanol is added into VII cell and carbon dioxide gas is introduced into the VII cell. So there is a cell in which we have to suppose to place the twin 61, cholesterol, glucose, PBS, and ethanol, and furthermore introduce the carbon dioxide. After magnetic stirring until equilibrium, the pressure is released to get the neosomal dispersion. So as in the VII cell, the pressure is increased due to the carbon dioxide. Furthermore, we have to suppose to release the pressure in order to get the neosomal dispersion. So this method enables one-step production and the easy scale-up. It utilizes the principle of supercritical carbon dioxide fluid. So this is about the supercritical carbon dioxide fluid method. Let us move towards the bubble method. Bubble method, it is yet another method which is used for the preparation of Niosomes. So in this method, the surfactant, additives, and the buffer are added into the glass flask with the 3 necks. Niosome components are dispersed at a 70 °C and the dispersion is mixed with the homogenizer. After that, immediately the flask is placed in a water bath followed by the bubbling of nitrogen gas at 70 °C, and that's why it is said to be the bubble method. The nitrogen gas is passed through a sample of a homogenized surfactant, resulting in a formation of a large unilamellar vesicles. So this is about the bubble method. So in the case of bubble method, surfactants, additives, and the buffers are added into the glass flask with the 3 necks. Niosome components are dispersed at a 70 °C, and this dispersion is homogenized. After that, immediately the flask is placed in a water bath followed by the bubbling of nitrogen gas at 70 °C. The nitrogen gas is passed through the sample of homogenized surfactant, resulting in a formation of a large unilamellar vesicles. These are the few methods which are widely used to prepare the Niosomes. Let us move towards the drug loading. Let us see the drug loading methods. There are two methods are there by which we can load the drug. That is, very first one is the passive loading and second one is the active loading. In the case of passive loading, the drug is passively encapsulated inside the neosomal vesicles like a liposome. So during neosome formation, the drug is included in the hydration step, in which the hydration is carried out using the phosphated buffer saline containing the predetermined concentration of drug. To reduce the size of formed neosome, the sonication could be applied during the hydration. So passive loading simply in the preparation method itself, either in the organic phase or in the aqueous phase, we are adding dissolving the drug. That is the passive loading. In the case of active loading, the active loading refers to encapsulation of the drug molecules into the neosomes with the help of transmembrane gradient. Already we have discussed the transmembrane gradient method. The drug passes through the neosome membrane by diffusion and accumulates inside the neosome by the protonation. Compared to passive loading methods, the main advantage of active loading method is its high drug loading efficiency. So active loading with the transmembrane pH gradient method and active loading with the transmembrane ion gradient method, these two methods are widely used for the active loading of drug into the neosome. So this is about the drug loading methods.